Hello, ladies and gentlemen. It's a beautiful Saturday afternoon in early October, and I really hope that you're outside enjoying it. But don't you worry, I got your back. I'm here for you. It's Saturday afternoon, and I'm inside recording a physics lesson just for you. So let's get started. You see the title on the screen, Acceleration and Displacement. We actually want to start with considering what we know about velocity. Okay, so let's just take a humdrum velocity here, like 8 meters a second, okay? And what that tells you about the ground covered each second, okay? Hidden in that piece of information about velocity, okay, and we'll assume a positive 8 meters a second, right? So we're going to the right. Typically on a piece of paper, to the right is positive. So we have a velocity of 8 meters a second. Now if you think about the ground covered, okay, the distance covered each second, right? We could illustrate that this way. Oops, let's get a line, right? In the first second you cover that much. Oh, hey, look at that. And what? Oh, yeah. Each second, right, I cover the same amount. That's what 8 meters a second means. It means that each second you cover 8 meters. Okay? Like so. And if the numbers aren't so obvious, right, or if you're given a word problem of some sort, you do have a tool in your toolbox. It was the first tool that you were issued, so to speak. And it's the first equation on the board in the classroom. It looks something like this. Okay, so you have this tool to help you solve for problems in which you want to know how much ground you've covered moving at a constant velocity, or some other aspect of it, right, like the time given the velocity and so on. But what we want to consider today is how much ground would I cover if I'm accelerating, right? So if I were to make an illustration of that, I think you could come to the idea that, because right when I'm accelerating, I'm not moving at 8 meters a second every second, right? For example, let's take a very easy acceleration here, right? If I have an acceleration of 1 meter per second squared, right? Then in the first second, we're going to look at the velocity now. At the first second, right, I'd be going 8 meters a second, okay? And then in the second second, I'd be going 9 meters a second, right? I'd be adding 1 meter per second to my speed. In the third second, I'd be moving 10 meters a second, and so on, okay? So my speedometer is increasing in value, but what about the ground covered, right? What about the odometer part, okay? I think if you reflect on that for a minute, you'll realize that you'll cover a certain amount of ground in the first minute, or excuse me, in the first second, right? But won't you cover more in the second because now you're going faster, and even more in the third, something like that, right? In other words, the displacement, or the distance that you cover each second, is going to grow, and we need an equation for that, okay? We do have an equation for how to figure out our velocity with respect to time. And I'll come over here and write that. You'll see later why I'm writing it here. But basically, right, that's this one. And remember that that's just the moved around version of your acceleration equation. Okay? In fact, I could use this very simple equation over here, right? I picked these numbers so you could do this in your head, but watch, I could actually do this with an equation. Okay, let's say I started at 8 meters a second, and I wanted to know how fast I was going 2 seconds later if I had this acceleration. I can actually use this formula here, right? I can say V equals, I started at 8 meters a second, and my acceleration was 1, and I did that for 2 seconds, right? I just plug the numbers in from here, and you see that I get 8 plus 2, which is 10 meters a second. Of course, we didn't need the equation here because we picked easy numbers we could do it in our head. But again, we do have a tool for that. But again, back to our original goal for today, we don't have a tool for how much ground I cover. Okay, so now I'm going to present that tool to you. And remember, in physics, equations are just tools. So I'm going to write that equation right here. This is the equation that you've probably already seen on the board. Okay, and it is the equation that tells you or allows you to calculate how much ground you will cover each second, or for whatever period of time you choose. Now, I know this looks a little intimidating to students at first glance, okay, but I'm actually going to make it easier for you. Let's go through what each of these means, okay. So I'm going to write D. Now this here just tells you your position at the beginning of the problem. Let's assume we start at the origin. Let's make it real easy on ourselves. Right? Physicists, whenever possible, they make the origin one of their start or ending points. That's going to make your math a lot easier. Well, if you start at the origin, your initial position is 0. And then we're going to make it even easier on us. We're going to make this be also 0, right? We're going to start from rest, so that makes that whole term 0. And now you see that this kind of intimidating looking equation now is looking a little bit better. Okay, let me write all that as 1. See, that's not so bad, right? And if if we want to tie in math knowledge now, I'm going to write this right here. This is really these two equations are the same type of equation, right? So if instead of D I had Y, if instead of K I had 1/2 A, see, this is a parabolic equation. And the really cool thing about this, right? The really cool thing about this is if we come now to our motion graphs and you think about what kind of motion, what kind of graph do I get for accelerated motion if I start at the origin at 0 speed? Well, you get a steepening curve. Well, what kind of curve do you get? Oh, hey, to the power of 2, I get a parabola. Right? So all this time you've been drawing curves, steepening curves and flattening curves, you've actually been drawing parabolas. Okay? But I know you can barely contain your excitement, but look, it gets even cooler. Check out, if you remember, what the corresponding velocity time graph is to this curved position time graph. It's actually we can do better than that here. Let me get a real line going. If you remember, it's right, a straight line rising. Now, why is that cool? Because look at the equation I wrote next to it. Look at the shape of this equation, what shape this equation has. It has the same shape as, oops, wrong color. It has the same shape as the equation that you know to be the equation for a line. Okay, if we make v, y, and that the y-intercept, and that the slope, then this is, oh hey, wait, that is a straight line. Right, so the equation of this line that you've been drawing all along is this equation right here. Right, and the equation for the curve that you've been drawing all along is this equation right here. Isn't that cool? These equations, see, students think these equations come out of nowhere, right? Oh, teacher just wrote them on the board. No, they are the equations of this motion right here, okay, that you've been drawing and you've been getting familiar with for quite some time. We don't want to be incomplete here, so we're going to come to acceleration time graph. Ka-chow. There you go. And of course, this is a very simple graph, right? There's not really an equation. I mean, there is, but it's not very useful to us, right? It's just A equals some constant. It's just like some number, 5 or 10 or 1. In this case, it's 1, right? Because we've been working with this 1, so we might write 1 over here, something like that. So there is, if you go on in physics, you're going to consider situations where acceleration is not constant and where there will be an equation here, right? But that's for a second year course or later. For our course, we're never going to have motion that's not constant acceleration, and what that means is we'll never have motion where this graph is not a flat line. Okay, it would be a positive flat line, a 0 flat line, or a negative flat line. But all of this motion and these equations here, right, are based on constant acceleration. Okay, now if you're not having fun yet, boy, I don't know what fun is for you guys. Well, let's see what else we can do here. There are a few more things we can do with this equation. Okay, this is actually a pretty nifty equation. I'm going to show you down here. What if we didn't have accelerated motion? Right? What if the acceleration was 0? Okay, so I rewrote the equation there. What if the acceleration is 0? Would you agree that this whole term goes away, this whole term becomes 0, right? Because a equals 0 makes this whole thing 0. And if you started at the origin, right? Let's say you started at the origin. Look what kind of equation you get here. Do you see that this equation here is exactly like an equation you already know, which let's move it around for you. Let's make it, we'll divide both sides by t. Hey, wait a minute. I've seen that equation before. It's the one up here. Okay, so I actually have written this equation on the board just kind of like as a extra help for students who don't immediately see that this equation is actually contained within this equation. Okay, but we really don't need this equation here, right? Because this equation is a simplified version of this one. This is a very nifty tool. Okay, the last thing I'm going to show you today is one more tool in the toolbox. It turns out that if we take our new displacement for an acceleration equation, okay, and we combine it with our equation from last time. So let's see here. If I have this equation here plus this equation here, okay, and if I basically take this second one, okay, and I plug it into the first one, okay, and the way I would do that is I would move this equation around until it said t equals, okay, oops, forgot the square here, right? In fact, when I move this around, it says t equals v minus vi over a, right? What I would do is I would take this whole thing and I would plug it into here where that t is, and I'd also plug it into here where that t is. And it turns out when I do that, okay, fortunately I will spare you all that nasty algebra. However, those of you who are so inclined, I'll be happy to give extra credit for anybody who wants to work that out on paper, algebra. What we're going to get actually is we're going to eliminate time out of this first equation, and we're going to come up with a brand new equation, okay, and it looks like this. Okay, the square of the final velocity equals the square of the initial velocity plus 2 times the acceleration times the change in displacement. And this is actually a really nifty tool because it doesn't have time in it, so you can solve some problems where the time's not given. In fact, it ends up being a shortcut. There are a lot of times where you could do in 2 steps with you could use equation 1 and then equation 2, or excuse me, equation 2 then equation 1. It just depends on the order. And that's a 2-step process. Or instead of using those 2, you could just use this one. Okay? So that wraps things up, and what you have now is you have all of your 3 essential kinematics equations, right? You've got this nifty little shortcut here, okay? You have this one that you brought with you into this lesson. It tells us what basically the definition of acceleration, right? Of velocity change over this time. And then we have our new displacement equation with respect to time, okay? How the amount of ground that we cover changes as time goes on if we're accelerating. That wraps it up.